Everybody, my name is Uwe Muhlich and I would like to present about a strain gradient approach for describing quasi-brittle failure. Allow me to introduce to you the problem first. When we are talking about quasi-brittle failure, for instance, in concrete, in structures of concrete, what are the things we observe? So first of all, we observe an evolution of damage prior to final failure. Furthermore, what brings us, or if we have a look at a typical load displacement curve, so we have an elastic regime and then a kind of hardening regime and softening. This is similar to what we observe, for instance, in plasticity. What allows us to classify this as quasi-brittle is the unloading path which goes back to the origin. We observe side effects in the sense that smaller is weaker. There's a nice illustrative explanation which goes back to Bajant, because the damage zone is actually related to length properties of the microstructure of the material. So if we have two specimens of different sizes under the same, let's say, nominal load regarding the fracture zone, so a smaller specimen will fail first because in relation to the specimen size the damage zone is so-called bigger, which is not, because in both cases the damage zone is actually more or less the same, but the small specimen, for the small specimen, the damage zone will reach the surface, so to say, faster. So if we aim to describe this problem by means of a continuum approach, this continuum approach has to account for deterministic size effects, and it should ensure that we do not observe spurious results due to softening. And this leads us to the conclusion that only a continuum model within the framework of generalized continua is suitable to describe this phenomenon. Regarding the laser, we have a lot of options to choose. We could choose for non-local elastic material or for strain gradient elasticity in the spirit of Mindlin and Eschel, or micromorphic elasticity, and there are even more. Here we chose to go for a strain gradient elasticity developed by Mindlin already in the 60s. The first step, after choosing the generalized continuum we would like to use in order to describe quasi-brittle failure, the next step is to relate the strain energy density of this theory to the undamaged material. Here we have again different choices. We could go for effective medium theory, which goes back to Kroner and Willis and co-workers, or we can use the so-called polynomial approach, which goes back to Golaganou, Forest, and others. The polynomial approach is bold, or is printed in boldface, because this is the choice we are making here. Having this, for the undamaged material, we focus, or what we like to do is, we would like to develop a continuum damage model based on this strain energy density by, for instance, applying thermodynamics of internal variables to get an evolution of damage into the model. strain gradient elasticity has been addressed today already at least 2 times. That's why I just repeat the cornerstones of this approach. It is based on an extension of the strain energy density, which usually depends only on the strains, by, for instance, the gradient of the strains, defining corresponding stresses, the usual stresses, as the derivative of the strain energy density with respect to the strains, and higher order stresses in the similar fashion, but as a derivative of the strain energy density with respect to the strain gradients. Now we can go and apply principle of virtual work or variational methods in order to work out eventually equilibrium conditions. The kinematics have been defined already here at the very beginning, and we need constitutive relations which are related to these 2 equations given on the right hand side above. Here for a linear material behavior, and also for a very special case, I will come back to that, which does not contain any cross terms between stresses and higher order stresses. This is only justified in certain, under certain conditions. And additional to the usual boundary conditions for displacements and surface tractions, we have so-called higher order boundary conditions. Why are we using strain gradient elasticity in the first place? The reason is rather simple, because we are using it because we know a method by which we can relate the microstructure to our constitutive equations by a homogenization procedure. And what we apply here is we take out such a volume element. In our case, this is an elastic matrix with a pore, and apply boundary conditions in, or expressed by overall strains and strain gradients, defining a porosity or a void volume fraction as the quotient between the radius of the void and the radius of our volume element. We can solve this boundary value problem, and from the solution of the boundary value problem we find a relation between average stresses and average strains, as well average strain gradients and higher order stresses M, where the constitutive relations here, these are the classical relations for porous elasticity. On the left hand side, on the right hand side, we see that this higher order material or constitutive tensor, which is of 6th order, not only depends on the elastic properties of the matrix material and our void volume fraction, but in addition it depends also on a length capital R, which is here the outer radius of our volume element, or you can interpret it as a mean distance between voids, for instance. From this we get...
Sorry,
yeah?
What is V or mu there?
Which one you mean?
Sigma equals CE.
This?
Yeah.
This is let's say average stress.
Yes.
We prescribe average strain,
Yes.
and we get the elasticity law between these two, which
the
T.
mu there, the second.
This one. This is the Young's modulus and Poisson number of the matrix.
Okay.
And in addition we get, so to say, the porosity. Yeah? And here you have the same quantities, however you get an additional length scale in it.
So you assume this isotropic.
Yeah. Actually we are going here for the most simple case we can imagine. It's a plane problem even. It's not even 3-dimensional. But the nice thing here is that eventually we get out an analytical solution which helps us to interpret the results at this stage more transparently, let's say. Okay. So this is, I'm showing this because this is one way to get the strain energy density for strain gradient elasticity and relate the additional, let's say, constitutive relations directly to the microstructure. Now this is the aim, not to have just a strain gradient elasticity to describe phenomenologically the problem, but to relate it to genuine properties of the material. Therefore, we opt here for such an homogenization procedure. This is the most simple, I would say, case we can consider, but we can do better. For instance, we can do it in 3 dimensions, and here we didn't go for solving this problem analytically as before. Actually, we are prescribing the same kind of boundary conditions here. Displacements, a displacement field at the boundary which can be expressed by the mean strain or the average strain and average strain gradients. But we obtained, or we didn't solve it in the same fashion as before, but we tried to get bounds for the higher order elasticity tensor in terms of Vogt bound and Royce bound. This was actually possible. As long as we are talking about isotropic behavior, we have an isotropic 4th order tensor as we have in general elasticity. In addition, we have an isotropic 6th order tensor which relates the higher order stresses and the strain gradients. An isotropic 6th order tensor has usually 5 independent parameters. It turns out, if we apply this kind of homogenization procedure, this reduces to 4 independent material parameters, here given by the eta 1 to eta 4. And you see that these parameters are again expressed by the Lamé constant of the elastic matrix, which surrounds the void, by the void volume fraction, which is here in this beta bar. And again, we have this additional length scale, the r squared, which is here the outer radius of this spherical volume element we are considering here, is in these equations. So this is a second way to obtain the strain energy density for strain gradient elasticity directly related to genuine properties of the microstructure. There are other possibilities, but having this, the question now is how can we develop based on this damage model? And here we borrowed an idea which is very common in linear fracture mechanics. It goes as follows. Assume we have such a volume element here and with a prescribed displacement field, and this volume element is under a lot of stress and starts claiming that it doesn't take it anymore, and we say, okay, you can relax, but the only option you have for relaxing is you let the void, or this void has to grow. You put this volume element under stress, so to say, by means of displacement or prescribed displacements on the boundary. The volume element suffers and says, okay, I need relaxation, and we say, okay, but we won't relax on the boundary conditions. The only thing you can do for relaxation is let the void grow. And we envisage the following mechanism for this void grow. We envisage that we have here the evolution of microcracks starting from the surface of the void. This implies a degradation of a certain part of the material. this way we come from this state 0 to a state 1. And this initiation and growing of microcracks requires work. This work or energy, and this energy is taken from the strain energy of the volume element. So we can write down the energy balance, taking into account now for the capacity to withstand load, not the original void anymore, but a bigger void. Huh? That's the basic idea. Now we can apply the general or the usual formalism from thermodynamics of internal variables. We define a free energy density, which depends on strain gradients, and void volume fraction. Introducing a variable gamma to take into account of the hardening behavior. In addition, we define a damage potential, and similar to what we use in plasticity, we have a case differentiation between loading and unloading. If this damage potential evaluates to a value smaller than 0, then we don't have a damage evolution. But if it evaluates to 0, then we have an increase of our void volume fraction expressed here by this F dot. So this, of course, this volume fraction we find here as before in these two elasticity tensors, which change in the course of loading. Let me show an example in order to check if this method really does what we would like it to do. We consider such a stripe with a small zone which has different material properties than the rest. We pull this on both sides. This actually becomes a one-dimensional problem. Here you see the respective boundary conditions and our, so to say, damage function. This problem can be solved without facing all these difficulties we have, because the incorporation of strain gradients, because in one dimension it's much easier to use so-called Hermite elements, so continuity requirements we can fulfill here easily. And we did it in MATLAB, which shows you another problem we face in quasi-brittle damage, which are so-called snapback problems. If we load now this bar, then we see here the elastic regime, then it becomes a nonlinear, and at a certain point it snaps back with a continuing damage evolution, and the stresses eventually reach 0. Then the damage is like that this bar doesn't withstand any load anymore. Sorry, I forgot. Of course, since we have an additional length scale here, we can vary the size or the ratio between this zone, let's say this pre-damaged zone or zone with different material properties, and our length scale, which could be interpreted somehow as the average distance of the voids in the original material. And we see here at the macroscopic level, let's say in the force displacement response, there is a difference, but it's not even that big. Bigger differences we see here when we look at the local, or the value of the void volume fraction, or damage if you like, as a function of location. If we vary the let's say the capital R, which is our internal length scale, if the length scale is small, then you see here a much more localized damage in the center of the bar, which is smoothed out as the R increases. Huh? So although, let's say, the general philosophy of attacking the problem of quasi-brittle failure seems to be clear, there are a lot of problems still to solve in the future. One problem is the discussion about this homogenization procedure in general. There's a lot of discussion going on. The most, let's say, rigorous scheme I know for random materials is based on the work of Willis and co-workers who did it in the context of random elastic composites. This is, in my personal opinion, one of the best strategies I've seen. There are actually already intents to bring this to the case when you have a viscoelastic matrix, not just an elastic matrix, by means of correspondence principle of viscoelasticity. This is something I'm personally interested in, since the goal now is to apply these kind of methods or models for asphalt materials which show a pronounced viscoelastic behavior. Finite element implementation strategies are still an issue, and also verification strategies, as well as numerically as well as experimentally. Here in the open questions I put some points. For instance, if you would like to use this effective medium approach or random composite approach from Willis and Dragon, so we would need to correlate a sieving line for concrete with a 2-point correlation for our model. This point I already mentioned, that we would like to go for viscoelastic matrices, but there are still a lot of open questions how this should be done. And homogenization methods in general, I also mentioned this already, in terms of rigor, consistency, and interrelations between, for instance, this polynomial method and effective medium theory. At least I see there a lot of, or a big need of discussions to figure out if these two approaches are even compatible. I'm sorry, yeah, with this, I'm at the end of my talk. Thank you very much for your attention.
Questions? Ask.
Sure, the last one, the fourth to last one. Yeah, that is one. So S is the dimension of the zone with the reduced strength, right?
Yeah. We reduce the strength in such a zone in order to force localization of damage.
Yeah. So if you have, you have considered a case where your internal scale length is larger than the damage, so the initial damage.
Yeah. Yeah.
And,
yeah. Here it's half of it.
Yeah, this is half of it. That's what but it seems a little bit strange. You have an area where you have a reduced initial something, but it is smaller than internal scale.
Yeah.
And also another thing, why the damage goes to 0 at the borders?
No, it doesn't. It goes to the initial value. No, not even this.
That's not it.
It's not 0.
Yeah, okay.
It increases here as well, but it's a symmetric problem. We would even just use this. One remark to your critics here. It's correct. It seems strange, but the idea is actually to let it go to 0. Then we have the original Cauchy continuum, and then this thing here goes beyond bounds. Then you have really a localization zone of dimension 0. This was the intention from this drawing.
Again, okay. You mentioned that your approach is for
brittle materials. Why it can be used for ductile materials? Could you explain in your approach? Could you apply this approach to ductile materials?
This has been done already. I mean, it is some. The ductile approach is more difficult in terms of because then you need a yield condition and a flow rule. But this has been done already. I mean, there's a nice contribution from Gouleganu and Leblanc from the 90s. They didn't compute the effective elasticity tensors, but they computed a yield condition for this volume element, based on a very classical approach, limit load analysis, assuming a kinematic mechanism due to plasticity, and then computing a yield condition, based on this yield condition, a flow rule.
The approach of Gilles Frankfort and Jean-Jacques Barigour. So it's also for brittle materials, so the minimization of some functional, they can understand how the structure moves.
So they do not use
But it's also, I think this question is related to mine.
Okay.
Can you give us more details about your homogenization?
Yeah. Okay. Yeah.
It is crucial.
Usually, in the usual representative volume element homogenization, you say you have a big volume element and the boundary data do not matter. And for random materials, you prescribe, let's say, or constant surface structures or linear displacements in order to get, and you solve the boundary value problem. You can compute or you can define what average stresses mean to you. So it's the integral of the stress fields, stress field over your volume element. This is this. And you prescribe a displacement field which is directly related to average strains, and you can show that if you compute the strain, the integral of the strain field over your volume element, that this coincides with the capital epsilon, with the average strain, so to say. So average strain is related to average stress. Now the idea, which is actually from this paper, from this work from Gouleganu and Leblanc, was, this only gives Cauchy continua. So which means we can relate it to a microstructure, but only by densities, only by specific values. And they came up with the idea to say, no good, we don't prescribe a linear displacement field at the boundary, but a quadratic one, and we relate these coefficients of this polynomial here at the boundary with the strain gradients. Then you do the same. You solve the boundary value problem and you define, actually, this is not an arbitrary definition. You can show that how you have to define your, in this case, your higher order stresses. This is stresses multiplied by location. And you can relate this to the strain gradients. And this relation is expressed then by a 6th order tensor. So it works actually in the same way. Instead of prescribing a linear displacement field, you prescribe a quadratic displacement field. You solve the boundary value problem, which is a purely elastic problem. And then you obtain the average constitutive relations. Does this answer your question?
So F is another mathematical parameter.
Now F is actually the void volume fraction, the porosity, so to say.
Until you don't have damage, it is given.
Yeah.
Or it is evolving with the shape.
No, it's given. As long as we don't incorporate damage, then it's given. We incorporate damage in order to make this evolving. this is a little bit tricky, because what we say is, for instance, if in terms of damage, what we actually do is, you might remember that in the free energy density, for instance, we use the density of the material which does not change. What we do is, we say, this is due to microcrack evolution. For the load-bearing capacity, we just replace the genuine void, or the original void, by a bigger one. No? But this doesn't alter the density of the material, because we have only microcracks. Huh? But if you're talking how many stress is related to strain, then we say the damage evolution, or in terms of damage evolution, we express it, yeah, okay, the void is now bigger. Huh? If you have another material, or let's say another damage mechanism, this philosophy will change. Huh? This we applied only for, because we had porous, elastic materials in mind. Huh?
Okay.
So I have two questions. One is related to Jesper's question. So in the for the three-dimensional, you showed the void and the Royce count.
Yeah.
You elaborate on how you obtain the Royce bound in this case. I think void bound, you're applying those boundary conditions that you've written. In the case of Royce bound, how do you?
Yeah, in the case of Vogt bounds, we do this. In the case of Royce bounds, we have to relate it to stresses.
So what are the boundary conditions in that case?
The same, but we express it actually the same, but then we relate it to higher order stresses. So what actually, this is unfortunately not on this slide, therefore I go back here. We do the same, but we have to relate it to that, to these higher order stresses in order to get the Royce bound, which is the lower bound actually.
The second question was about your simulation of the bar problem. And in this simulation, again, what are the boundary conditions that you can get snapback, which means to me that you have two displacements of the same.
No, sorry. We prescribe actually the force. No, but we need an arc length method because it's not. This is not unique in terms of I give a force and I have only one displacement. This doesn't work. And it does not work either that you say you give one displacement and then you have only one force. No? And this is because we pump up the structure with energy, and the energy release due to damage is quite severe. In plasticity, it goes usually, plasticity is much better. In plasticity, due to dissipation, due to plasticity, you have something like this. So you have always a displacement, or to every displacement you can relate uniquely an applied force. And in these problems you cannot. So you need actually a full working arc length method. This is an established, these are established methods. But you have to program it. That's the only thing you have to do.
We have a question from the.
Actually, I'm not very familiar with strain gradient approach, so it was very clear presentation, so thank you very much.
You're welcome.
For all the nice explanations.
You mean this?
I want to ask very basic questions,
Yeah.
which will be the first two are kind of basic. You mentioned that you have 4 independent material constants. So you have 4 independent material constants in your formulation?
Only for the gradient part. Yeah, no, yeah. Good question. Good question. We have two. Let's say we start with 3 material parameters in the classical setting. We have the porosity here, and we have Young's modulo, or we have two elastic constants for the matrix material. Now, if we go from the classical approach to the strain gradient approach, we have 4 additional parameters more. That's why this is hard to measure. Huh? So that's why, in my personal opinion, it is important to try to relate these parameters by homogenization methods to genuine material properties. And here you see, the question is now, we have this relation, we should verify it experimentally. This we didn't do yet. No? But the philosophy is, the homogenization helps us to interpret the material laws, not just that we have to assemble experiments to fit parameters, but what is the meaning of these parameters in terms of void volume fraction, mean distance between voids, and so on. Huh?
Okay. And also, there is this landscape parameter R. So again, how do you specify the parameter? Is it something to do with tendency on the side, or do you need to calibrate somehow?
You have to calibrate it somehow, because when we are talking about random materials, you can talk about an average distance of void, but this is really the ideal case. I would say there will be some calibration. What we intend to do in the future is that we do something very simple. We simulate a beam made of porous materials. We just put holes in it. And then we try to describe this as a one-dimensional strain gradient model. And if we get out the same, let's say, displacements at the end, we trying this. But I would say this can be, this will reveal certain differences. And then we have to adjust this model accordingly. This gives us only the trend. For a real material, we have to then start with the fit parameters and so on.
You have 5 additional parameters common case here. Because 5 additional physical constants here. Yes. My question is about for your variation, various functions which is solutions of gradient model. Can you see?
This here.
The previous, yeah, the second slide. The second slide. A variation problem. Yes.
This one?
No.
This one?
Yes, this one.
No.
Where is V and U as gradient solutions here? On the variations list. Where is here gradient solutions? When you variation, when here.
So I should start over maybe.
These gradient solutions depend from 2 parameters, scale parameters, which describe the exponential change in all gradient solutions. Not 5, but only 2 parameters.
Yeah, but maybe we let me just put this straight again so that we talk about the same thing.
Where is here straight gradient solutions?
This material is not a gradient material. No? This is a plain linear elastic material. No? So the behavior of this volume element S is described by a strain gradient approach. Huh? This is standard linear elasticity. So, and in the most general case, 3 dimensions, you say you have an isotropic material, you have 5 additional material parameters because of the character of this isotropic tensor. Huh? But if you do this, the thing is that due to the solution of these problems, it turns out that you have less. This can be because we have also an isotropic volume element. No?
Yeah.
Huh? This is, more.
Yes, but My question is about the gradient solutions very concentrated near the boundaries. The origin procedure very difficult because these solutions very concentrated in the bones, and it's difficult to average this problem.
Yeah, but I could. Yeah. This is a linear elastic material in the sun for the matrix. So I have actually. If I have this as a volume element and I draw, for example, the circumferential stress, I have such a stress field.
Yes.
And the averaging means computing the integral of this.
It depends from parameters which describe namely the changing of the solutions. Very strong dependent. Yeah. And common case 2 parameters. 5 parameters joined for 2 parameters common case. This point